Welcome to the fourth vodcast for special relativity, and this time we're getting into time dilation. You'll remember that the last vodcast we looked at the relativity of simultaneity, and we saw that people who are moving relative to each other won't agree on how far apart different events occur. So one person might say that two events occur at the same time, another person disagrees, or they'll disagree about the order of events. So clearly something's happening with the way people measure time when they're moving relative to each other. We're going to go a little bit deeper into that with this one. So you can see the goal there, what we're going to try and get out of this vodcast, which is to understand what time dilation is and be able to relate the time interval that's measured between two events occurring, relate that interval to two different reference frames. So one person measuring the time interval between two events, and then a different person in a different reference frame measuring the time interval between those same two events, and see how their measurements relate to one another. So again, we're going to continue considering trains because it's so creative. But it is simple, I suppose, so it helps. But we're going to introduce the idea of a thing called a light clock here. So a light clock it's again just a thought experiment, but it's something to try and simplify the way we think about this stuff. So this light clock, you need to imagine we have a light source which just shoots a flash of light, which we're going to just imagine to be like a little ball, a little photon perhaps. It hits a mirror and then bounces back. So what this is meant to be showing is that light leaving and then coming back to exactly the same place. I've just had to draw it slightly to the right so that we can see it obviously, but it's just going straight up and straight back again. And the idea of the light clock is because light travels at a predictable speed, we can kind of consider the time when it returns to the light source to be a way of measuring time. It's a bit like a tick on a clock. So when it gets back here, we get ticking on our clock. So let's just consider we've got one of these light clocks inside a train. So there's a light source here, there's a mirror up the top, and then when it comes back, this represents our two events. So event A is the light leaving at the light source at the bottom of the train. Event B is when that light returns to the bottom of the train. In exactly the same position. So in the train, anyone who's measuring this would say that event A and event B occur at the same position. But of course some time has elapsed. So what we're going to do is just relate what those times are. So we can say that using this good old relationship between distance, speed and time, we can say that distance 2d, now I'm saying 2d because the distance from the bottom of the train to the top is d, but our light is going to the top and then bouncing back again. So 2d is equal to the speed that the light travels at, and we know from Einstein's second postulate that the speed of light in all reference frames is c in a vacuum. And so we're assuming a vacuum here. So that's our speed. And then I'm just going to say delta t. So remember delta means change in. And I'm saying change in because it's the time that's elapsed, or a time interval between event A and event B. So delta t, and I'm just going to say naught, t naught. I'll explain the reasoning of that naught a little later. So hopefully that situation is simple enough and makes sense. So let's now think about exactly the same situation, but from the point of view or from the reference frame of someone who's standing on a platform and measures that the train is moving at a velocity v relative to them. So our train is moving along. I'm just going to kind of show that with an arrow here, v. And so this is showing the exact same thing, but measured from someone standing on the platform who says the train's moving at speed v. The height of the train hasn't changed, it's d. This is still event A. This is still event B. So when it gets to here, they say, okay, well, that's a tick of the clock. And the key thing to see here, though, is that this person measures that the light has travelled a greater distance, because not only has it gone up D and down D again, it's also moved to the right. And we can say how much that's moved to the right if we take V to be the speed of the train. So the distance from here to here should be, again, using this, distance equals speed times time. That's going to be the speed of the train relative to this person, times the time that they measure to have elapsed between event A and event B. I'm just going to call that delta T. I'm not going to use delta T naught because we need to be careful here now, as you're starting to realise that we can't assume that what this person measures to be the change in time is going to be the same as this. So that little naught was to distinguish this measurement from that measurement. But whatever this person measures to be the time interval between event A and event B, we call delta T, and this person measures the velocity of the train to be V. So V times delta T will give us how far the train has moved from here to here. So how far it's moved between event A and event B. It's also gone up D. So let's say that the distance from here where it leaves at event A to then where it bounces off the mirror and when the train's moved a little to the right, let's say that that is L, and just by the symmetry of the situation, this will also be L. Okay, so we can just write a couple of equations now to relate what's going on here. In the same sense that we said here 2D must equal C delta T naught, here we can also say 2L, so this path from here to here, that's a total distance of L, must be equal to C delta T. Now that's saying the same thing as what we're saying up here. But what you might be starting to realise is that we're encountering, again, what might seem like a little bit of a contradiction, which is that this is travelling a greater distance. According to this person's measurement, and it's absolutely correct, this is travelling a greater distance because it's travelling horizontally as well as vertically. But the speed of light doesn't change. It must still be C. So it's travelling a greater distance but at the same speed, which means you might be able to guess now what we're going to expect is that the time that this person measures is going to be greater. We're going to see how that works out with a little bit of maths in just a minute. So we've got this relationship. The other relationship that we can use is using Pythagoras. So to relate this length to D and to what we have here. So if you just imagine this triangle, this length is going to be V delta T divided by 2 because it's half of that. From here to here is D, so that's just the height of the train. So we can therefore say that L is equal to the square root of D squared plus V delta T divided by 2 squared. So at this stage, what I'm hoping you can understand is just the situation that we've described. I'm hoping that you're starting to get a feel for the fact that this person is going to have to measure a greater time that's elapsed because of the fact that they're saying the light has travelled a greater distance, but of course the speed is still c. And then what we're going to do now is combine these equations to try and get a relationship that relates these different things. So let's do that now. I'm just going to rewrite the three equations that we have here. So the first one was 2D equals C delta T naught. We also had 2L equals C delta T, and we had L equals the square root of d squared plus v delta t divided by 2 squared. So we can then say, if we combine what we have up here with here, so I'm just going to slightly change this one to say d is equal to c delta t naught divided by 2. So just using this to substitute for d here, I can rewrite our equation or expression for L to be c delta t naught divided by 2 squared plus v delta t divided by 2 squared. And now what we're going to do is take this equation and eliminate L with this equation. So I can rewrite this one as being L equals c delta t divided by 2. So I'm now just going to replace the L here with that expression. So c delta t divided by 2 is equal to the square root of c delta t naught divided by 2 squared plus v delta t divided by 2 squared. At this point, something I want to make really clear is you do not need to, in the VCAST study design, do this. You're not going to be required to prove this stuff. What you need to be able to do is just understand this idea to be able to understand why time dilation occurs. You might need to be able to explain this idea that in one person's reference frame they measure light travelling a greater distance than the other person, and because the speed of light is the same, then the time interval is going to be greater. You might need to explain that, and you will need to use the end result of what I'm getting to here to be able to do calculations. But the actual proof that I'm doing now, this algebra, is not something you would need to do or be examined on. But I think it's worth you just seeing where these things come from rather than having to accept the formulas. So I'm just going to slightly rearrange this by squaring both sides. So I'll have c squared delta t squared over 4 is equal to c squared delta t naught squared over 4 plus v squared delta t squared over 4. And now what I'm wanting to do is make delta t the subject. So I'm just going to bring this across first of all. So I've got, and sorry, I'm going to eliminate 4 from everything because everything's got that. So I'm going to bring this term over here. So I'll now have c squared delta t squared minus v squared delta t squared is equal to c squared delta t naught squared. And now take delta t squared out as a common factor. And now I'm going to divide that across into both sides. So delta t squared is equal to c squared divided by c squared minus v squared times delta t naught squared. And this can be rewritten if you imagine dividing through here. This can be rewritten as delta t naught squared divided by 1 minus v squared on c squared. So I've basically done that by dividing the top and bottom of this fraction by c squared. So if you divide the top by c squared, then this becomes a 1. If you divide the bottom by c squared, this becomes a 1, and this becomes v squared divided by c squared. And then finally, I just take the square root of all of that. So delta t is equal to delta t naught divided by the square root of 1 minus v squared over c squared. So, as I said, you don't need to do all that, but I think it's helpful to see where it comes from. You do need to know this, so I'm just going to explain this a little more now. So, a couple of definitions and then I'll come back to this equation. So we have this thing delta t naught, which we're going to call a proper time interval. So this word is unfortunate, but it's just the word that gets used. It's not supposed to imply that this is more correct, and so I don't want you to make that confusion. It's not more correct, but we just need a word to distinguish the two different measurements that are made. Both measurements are absolutely correct, but what the proper time interval means is the time interval that's measured between two events in a reference frame where those two events occur at the same position. So just notice back here, that was the case in the train. Event A and event B occurred at exactly the same position according to anybody who's in the train. It's a bit like if you're riding a train and you throw a ball up in the air and you catch it again, it left your hand, it came back to your hand. It was in the same place, even though by the time you catch it, the train's moved sort of forward. So according to someone else, they might not say it is the same place, but for you, it's the same place. And so that's what we mean by a proper time interval, when those two events occur at the same place. V, just to remind you, that's the relative speed between the reference frames that we're interested in. And so then delta t is the time interval in any other reference frame. So any other reference frame which is moving at the speed v relative to the reference frame that is measuring the proper time interval. So therefore, in this reference frame, the time interval is not measuring two events that are occurring at the same position. It's measuring two events that are not occurring at the same position. So then time dilation represents the idea that these two measurements are different. And so in particular, it's the factor by which this time measurement is greater than this time measurement. And that's important. I want you to realize that this time interval will always be a bigger value than the proper time interval. And we can show that mathematically, just coming back to here. We can show that mathematically because v is always a smaller number than c. Nothing goes greater than the speed of light. Therefore, what we have here, 1 minus this number, will always be some number that's less than 1. And whenever you divide by a number that's less than 1, you end up with a bigger number. So delta t naught divided by something that's less than 1, we're going to get a bigger number there. So I just want to introduce another definition here, which is the Lorentz factor. And so you might see from here the Lorentz factor is basically everything here without the delta t naught. We use the symbol gamma for that. So therefore we can kind of simplify this relationship using gamma, and this gives us time dilation. So that's basically the end of that vodcast. Just one thing that I might leave you with to think about is how does the person who's in the train explain the fact that this person seems to have measured two different times? So this person, remember, they have a clock here, and then here they've got another clock which is synchronized according to them, and it measures some other time. So you might remember in the previous podcast I spoke about having an array of clocks which are all synchronized to be able to measure events at different points. Well, this is exactly what I'm talking about. So the person standing on the platform would have had their clocks here and made sure they were all exactly synchronized, and then he or she can measure the time interval by comparing what the clocks read when those two events occurred. So how does this person explain the fact that they're measuring a different value to this one? You might like to think back to the idea of relativity of simultaneity again. So basically, does this person agree that these two clocks are ticking simultaneously? Obviously a loaded question there. Another thing you might like to think about is, what if we reversed it? What if the light clock was on the platform rather than in the train? What's going to happen there? There's some things that you might like to think about and things we can discuss in class, which are quite interesting. I hope this has been helpful. As you can see, the budget's expanding because we're using loose leaf paper now rather than exercise books, which is far more posh. But of course, if you enjoyed this vodcast and you'd like to donate to the efforts, then we'll set up some bank account details for you to be able to do that. Fantastic.